yesterday we had seen the modeling of B-Spline curves, and for the case when we said that n is equal to 5 and k is equal to 1, that means you have 6 points and the degree of the curve is 0. We had derived the expressions for the blending functions, and we had said that the blending functions would look like this. And so on. Sorry. Anyway. Okay, which means that this is n01, this is n11, this is n21, this is n31, and so on. And the curve, we said, if we have a set of 6 points, the curve is a discontinuous curve consisting of only these points. Okay, that means for the parameter u going from 0 to 1, the curve is concentrated at one point. From 1 to 2, it is concentrated at this point. From 2 to 3, it is concentrated at this point, and so on. Okay, this was in the case of B-spline curves with degree 0. That means when k is equal to 1. Okay, and for the definition of the B-spline curves, we had mentioned that any point on the curve will be given by this expression sigma pi nik of u, where nik is a blending function which depends on a parameter k, where k minus 1 is the degree of the curve. And for defining nik, we define it recursively, first defining ni1 of u to be equal to 1 if u is between two certain not values, where the not values are defined by these expressions. Okay, and for defining nik for higher values of k, that is when k is greater than 1, we said we will use a recursive definition, and Bezier curve was given by this expression, where nik is u minus ti times nik minus 1 divided by this expression, and so on. Essentially nik depends on nik minus 1 and ni plus 1 k minus 1. Okay, so this is a recursive definition we had given yesterday. Now let us take the case when we say n is equal to 5 and k is equal to 2. Okay, that means the degree of the curve is 1, first degree curves. Okay, so we are eventually interested in defining n02, n12, n22, and so on. Okay, so n02, if we take up this expression, I put I equal to 0 and k equal to 2. Okay, so n02 would become u minus t0 multiplied by n01 of u divided by t minus t0, sorry, t1 minus t0 plus t2 minus u multiplied by n11 of u divided by t2 minus t1. Okay, this is directly obtained from this expression, u minus ti with I equal to 0 and ik minus 1 with I equal to 0 gives me this term, ti plus k minus u with I equal to 0 and k equal to 2 gives me this term, and so on. Okay. Now to define the not values, in this case the not values, the ti's, we had seen them yesterday, and these not values will take values 0, 0, 1, 2, 3, 4, 5, 0 and 0. Okay. The not values are defined using these expressions. So whenever I is less than k, in this case k is equal to 2. Okay, so t0 and t1 will be equal to 0. That's what I have written here. t0 and t1 are 0. After that, when I is between k and n, that means between 2 and 5, it will be I minus k plus 1. k is 2, it will become I minus 1. Okay, so T2 will be 1, T3 will be 2, and so on till I is less than or equal to n. N is 5, so up to T5, T0, T1, T2, T3, T4, T5. At this point will be I minus 1. This is T5. Okay, after that it will be n minus k plus 2. N is 5, k is 2, so it will be equal to 5 after that. It will be 5 and 5. It can't be 0 after that, sorry. Okay, so the knot values will be 0, 0, 1, 2, 3, 4 and 5, 5. Okay, so whatever be my curve that is finally defined, I have 2 knots at the starting point and 2 knots at the end point. Okay, 2 coincident knots, that is. So if I put these values over here, I will get u minus t0 is 0, so u minus 0 multiplied by n01. Okay, if we take in the definition of n01, that is ni1 with I equal to 0 will be equal to 1 when u is between t0 and t1. Okay, so when it is between t0 and t1, so at u equal to 0, ni1 or n01 will be 0. Okay, and will be equal to 0 otherwise. Again, you said something?
Between this, it's 1 and
yeah, between this it will be 1, it will be 0 otherwise. So at u equal to 0 it will be 1, that is only at one point. At all the other points it will be equal to 0. Okay, so if we look at the complete range, we put that equal to 0 and this term will turn out to be 0 divided by 0. Okay, this plus T2 is 1, so it will become 1 minus u divided by T2 minus T1, T2 minus T1 is 1 multiplied by n11 of u. Let me just get expressions for n01 and n11. Okay, that will make it simpler to compute. So n01 is equal to 1 if u is equal to 0, it is equal to 0 otherwise. Okay, n11 will be equal to 1 when u is between 0 and 1. Okay, it will be equal to 0 otherwise. n21 will be 1 when u is between 1 and 2. Okay, n31 will be equal to 1 when u is between 2 and 3. n41 will be 1 when u is between 3 and 4. Okay, and finally n51 will be 1 when u is between 4 and 5. Okay, this is directly from the definition we had given earlier, this definition. Okay, when u is between two consecutive knots, it is 1, otherwise it is 0. Okay, that's how we are getting all these relationships. Okay, so if I put it over here, this is, I will write it here again, this is n01. Okay, and this is n11. Now n01, at the point u equal to 0 it is 1, otherwise it is 0 throughout the curve. So we will take it to be 0 throughout the curve right now, and n11 is 1 between 0 and 1 and is 0 otherwise. So this complete term n01 is 0, so this will replace this by 0, so it will come in the form of 0 by 0. And if you remember, I had mentioned that whenever we have 0 by 0, we will take that to be 0, we will take the limit to be 0. Okay, so this complete term will vanish, and this n11 n11 is 1 between 0 and 1. Okay. So between 0 and 1, this will be equal to 1 minus u when u is between 0 and 1. Okay, and it will be equal to 0 otherwise. Okay, so when u is between 0 and 1, n02 is 1 minus u, otherwise it is 0. Okay, so it is basically this term 1 minus u times n11. Is that okay? If we go to the next term, that is n03, sorry, n12. Okay, now again from this expression, n12 will get in terms of n11 and n21. Okay, so this will be equal to u minus 0 divided by 1 multiplied by n11 plus this will be 2 minus u divided by 1 multiplied by n21. U minus Ti, with I equal to 1, Ti is 0, and Ti plus k minus u, so you will get T3 minus u, T3 is 2, 2 minus u, and these terms will come out to be 1. Okay, so this is equal to u times n11 plus 2 minus u times n21. Okay, now this n11 n11 is equal to 1 in this range and n21 is equal to 1 in this range. Okay, so effectively what we will get will be that in this range, when u is between 0 and 1, n12 will be equal to u. Okay, and when it is in this range between 1 and 2, it will be equal to this expression. Okay, because when n11 is equal to 1, n21 has to be 0, and when n21 is 1, n11 has to be 0. Okay, so n12 will be given by this expression. Okay, similarly the other expressions, I will just write them down now. So n22 will be u minus 1 times n21 plus 3 minus u times n31, and 32 will be u minus 2 times n31 plus 4 minus u times n41, and n42 will be u minus 3 times n41 plus 5 minus u times n51, and finally n52 will be equal to u minus 4 times n51. Okay, the second term will have a term of 0 by 0, that will again be taken as 0. Okay, so the other expression we will get for n12, n22, 32, 42 and 52. So these are different shape functions we will get in this case. Okay, if we plot these shape functions, this will be n01, changing between 1 and 0. Sorry, the expression we had for n02 So n02 is 1 minus u when u is between 0 and 1. Okay, so between 0 and 1 it is equal to 1 minus u. So it is going to be a linear relationship with a slope of minus 1. So we'll get a figure like this. Okay, this is n02. If you take up n12, okay, n12 is u times n11. That means between 0 and 1 it will increase like this. Okay, it is again a linear relationship in the range of 0 to 1, and between 1 and 2 it will be equal to 2 minus u. So it will be like this, and the rest of it will remain 0. This is n12. Okay, this is 1, this is 0. Okay, again when I take n22 I will get a curve like this. This is n22. For n33, so 32, so this is n32. Okay, n42 will look like this. Okay, and 52 because the curve is defined only up to u equal to 5. Okay, so it will look like this. This is n52. Okay, n52 is given by this expression, u minus 4 times n51. Okay, n51 is 1 in this region and n52 will be this slope. Is that okay? Okay, now if you look at these blending functions, at any point of the curve we will find that only 2 points are effective. Okay, that means in this range between 0 and 1 only P0 and P1 will have their effect. Between u equal to 1 and 2 only P1 and P2 will have their effect. Okay, between u equal to 2 and 3 only P2 and P3 will have their effect. Okay, what that means is if you have a set of points, what will the curve look like? This curve will look like a set of straight lines. At this point you will say u is equal to 0, here you will get u equal to 1, 2, 3, 4 and 5. This is the first control point P0, this is P1, P2, P3, okay. So between these 2 points, between these 2 points u equal to 0 and u equal to 1, these 2 points have their effect. So the curve is a linear combination of these two. Okay. Similarly, between these two, the curve will be a linear combination of these 2 points. So we get a set of straight lines. Okay. Just to compare, when k was, this is the case when n is equal to 5 and k is equal to 2. When k was equal to 1, I had a set of points here like this. Okay, so when k is equal to 2, my curve is continuous, but it has only C0 continuity. Okay, for k equal to 1, the curve was discontinuous. Now when we take k equal to 3, we will get a quadratic curve or second degree curve. Okay, for k equal to 2, I have a linear relationship. All my shape functions are linear functions. Linear functions which are defined in a certain range. Beyond that range, the function is 0. Okay. So now let us take the case when n is equal to 5 and k is equal to 3. So if I say n is equal to 5 and k is equal to 3. the first thing we define are the not values. Okay, so the TIs, now the TIs will be 0, 0, 0, 1, 2, 3, 4, 4 and 4. Okay, again this is the same definition we have given for the not values. Okay. If I carry out the complete, if I find out all these expressions the way I did for n12, now I will have to find for n13 and so on. Okay. So I will get my definition of the curve P of u, that will come out to be, I am writing the expression directly now, 1 minus u whole square times P naught plus half of u times 4 minus 3u times P1 plus half of u square times P2, and this is in the range when u is between 0 and 1. Okay. This will be equal to, the curve will be half of 2 minus u whole squared times P1 plus half of minus 2u square plus 6u minus 3 times P2 plus half of u minus 1 whole square times P3. Okay, this is when u is between 1 and 2. Okay, this will be equal to half of 3 minus u whole squared times P2 plus half of minus 2u square plus 10u minus 11 times P3 plus half of u minus 2 whole square times P4. Okay, and finally it will be equal to half of 4 minus u whole square times P3 plus half of minus 2u square plus 20u minus 32 times P4 plus half of u minus 3 whole square times P5. And again this is when u is between 2 and 3, and this is when u is between 3 and 4.
Equality side only on the greater than side.
It doesn't make a difference because we have C1 continuity.
The function will be same.
Because since the functions are continuous, it doesn't make a difference. Okay, we can show that they are the same. Okay, I can either put equality only on one side or on both sides, it's same material. Okay. Now again, as we should have expected, since k is equal to 3, in any range of the curve we have 3 points which are effective. P0, P1 and P2 are effective when u is between 0 and 1. When u is between 1 and 2, P1, P2 and P3 are effective. Between 2 and 3, P2, P3 and P4 are effective. And between 3 and 4, P3, P4 and P5 are effective. Okay. What that means is, if we have 6 points like this, I have a curve which is defined like this. Okay. My knots will be defined at 0, 1, 2, 3 and 4. So this is u equal to 0, 1, 2, 3 and 4. Okay. For this part of the curve between 0 and 1, P0, P1 and P2 are effective. Okay. So for this part of the curve, these 3 points are effective. If I change this point, this part of the curve will not get modified. Okay. For this part of the curve, for this part, we will get P1, P2 and P3 will be effective. Okay. And then for this part, we will have this, this and this being effective. Okay, and finally for this part, okay, we will get this point, and this point being effective. Okay, so again if I change this point, this portion of the curve will not get changed. However, the rest of the curve would change. So if this point is moved from here to here, my curve will probably get modified to something like this. It has to maintain C1 continuity here. Okay, so my curve would look like something like this. Okay, this portion of the curve will remain unchanged if I move this point. Okay, this is the first thing that is important in terms of the B-spline curves. We get a local control, the curve will get modified only in a certain range.
This is C1 continuous.
This curve will be C1 continuous.
First derivative.
Yeah, the first derivatives will be the same here. That is, I said the slope would remain the same at this point. Okay. Now the next thing that we will do, if you look at these expressions, there is a certain pattern in these expressions. Okay, we have P0, P1, P2 here, P1, P2, P3 here, P2, P3, P4 here, and so on. Okay, so what we will do is, this is the case when n is equal to 5 and k is equal to 3. Okay, let's first draw the blending functions. Okay, in this case, the blending functions this is n03. Okay, n03 is going to be a quadratic function starting from 1 going down to 0. Okay, if I take n13, let's say it will start from here. Okay, actually the peak is slightly earlier. Okay, this portion of the curve. This is n13. Okay, we look at n23. This is n23. Okay, if I look at n33, this will be n33. Okay, it's a quadratic function, symmetrical about the center, just like n23, which is also symmetrical about the center. Okay, but n13 is not symmetrical, n03 is also not symmetrical. Okay, n43 would be similar to n13 now. Okay, so n43 it peaks slightly beyond the center. This is the center for n43. It peaks slightly beyond this. Okay, and finally n53 will look like this. This is n53. N53 is a quadratic function between these 2 points, 0 before this. N43 is a quadratic function between these 2 points. It's one quadratic function here, second quadratic function here. Okay, and is 0 before this. And 3 is also a set of quadratic functions, but it is symmetrical about the center. N23 and N33 have the same shape. N13 and N43 are somewhat similar but mirror images. And N03 and N53 are also similar. Okay, this is for the case when n is equal to 5 and k is equal to 3. Okay, so far in changing the value of k, okay, we said that when k was equal to 1, we got 0 degree curve. Well, for k equal to 2, we got a first degree curve. For k equal to 3, we are getting a second degree curve, and all our blending functions are quadratic functions. Okay, but what happens if I increase my number of points? If instead of n equal to 5, let's say I take n equal to 10, what does one expect?
The shapes of the function will get more and more closed.
The shape function will get more and more.
The function n
Yeah.
will get more, will look more complicated or more.
In fact, no. What would happen is if you change k, the geometry of this function will become more complex. It will become a higher degree curve. Okay, but if I change n, it will still remain a quadratic curve for k equal to 3. But since the degree of this curve is determined by the value of k, okay, so it will always remain a quadratic curve. Okay, so what will always happen is that at the starting of the curve, I will get one shape function like this. The next shape function will be like this. The last shape function will always be like this, and the last but one shape function will always be like this. Okay, except that instead of that being at u equal to 4, it will be at some other value of u. Okay, but the intermediate shape function will all be similar to this. Okay, so all my intermediate shape functions will look like this, symmetrical, except at the ends. Okay, so if we consider a portion, okay, where let's say if we have many points, okay, we have one shape function like this. The shape function for the next point is going to be staggered and will be like this, and the shape function for the next point will again be staggered and will be like this. This is how we will get a 3 successive shape functions or blending functions. Okay, should use the term blending functions. Okay, so the 3 successive blending functions will look like this, except at the ends. Okay, so what we can do is, except at the ends, we can write an expression for the curve in terms of these general shape functions. I can have, let's say, I points on this side, and I can have any number of points beyond this. Okay, and if you look at these expressions are in some sense repeating. P0, P1, P2 here, P1, P2, P3 here, and so on. We have 1 minus u, 2 minus u, 3 minus u, and 4 minus u over here. U, u minus 1, u minus 2, and u minus 3 over here. And even in this term, there is a certain pattern. Okay, I will just write down the expression for that pattern. You can verify it later on. If I take a case where n is any general value and k is equal to 3, okay, then we can say that P of u will be equal to half of I plus 1 minus u whole square times Pi plus half of, this is u minus I plus 1 multiplied by I plus 1 minus u plus I plus 2 minus u multiplied by u minus I. This whole thing is multiplied by Pi plus 1, and this plus half of u minus I whole square times Pi plus 2. And this is the definition of the curve when u is between I and I plus 1. Okay, and when I takes any value between k and n. Okay, if I takes a value smaller than k, then this is not correct. Okay, because if the I takes a value smaller than k, then we'll have these shape functions coming in, these shape functions which are not the same as the other shape functions. Okay. So we have this expression, and now what we will do is in this expression we will put, let us say, u prime to be equal to u minus I. Okay, if we do that, P of u will be equal to, or let us say, okay, P of u prime will be half of 1 minus u prime whole square times pi plus minus 2, this is u prime squared, plus 2 times u prime plus 1 times pi plus 1 plus u square times p of I plus 2. Okay, all I have done is I put u prime equal to u minus I in this. Okay, so u minus I becomes, so u prime squared, and from here u minus I will become, this will be u prime plus 1, and this will become 1 minus u prime. I can expand that to get this expression. Okay, and this is valid when u prime takes any value between 0 and 1. Okay, I have u taking a value between I and I plus 1. Okay, so u prime will take a value between 0 and 1. Is that okay? Okay, what I am effectively doing, okay, firstly why I am doing it. See, if I have a set of points, 6 points let us say, and I have a curve between this, my not value are defined like this: 0, 1, 2, 3, 4. Okay, so this is the value of u equal to 0, u equal to 1, 2, 3 and 4. Now I will define each portion of this curve, I will call it a separate curve, and I will say my u prime is changing from 0 to 1 here, to also changing from 0 to 1 here, and 0 to 1 here, and so on. So in each portion I will have a different parameter which will be varying from 0 to 1. Okay, because I have said u prime is u minus I. Okay, so if in this case I is equal to 1, so u prime will vary from 0 to 1. Again u prime will vary from 0 to 1 here, and so on. Okay. So I get this expression, and we will rewrite this expression as, now instead of u prime I will again go back to u, okay, just for the sake of convenience, and let us say P of u will be equal to half of u square u1 multiplied by 1 minus 2 1 minus 2 1 minus 2 0 1 0. Okay, so this expression I can rewrite it in this form. Okay. Or I say this is equal to, let's say uk. If you remember in the case of PC curves, we had a matrix like this, so u cube, u square, u1. Okay, so in this case you have a second degree curve, So we have terms only up to u square. If you have a third degree curve, we will have terms going up to u cube. So this matrix U depends on the value of k. Okay, size will be k. There will be k elements in this. In this case, k is equal to 3. Okay, multiplied by mk. This matrix is a M matrix, and this matrix is what I will call a P matrix, which is pk. In some sense, this is a geometry matrix for the curves. Okay, let us say for this curve, my geometry matrix will consist of this, this, and this point, for these 3 points. Similarly, for this curve, my geometry matrix will consist of this point, and this point. Okay, and this is for the case where k is equal to 3. Okay, we can similarly derive expressions for the case where k is equal to 4. Okay, and what we will get will be, this will be equal to 1/6 of, this will be u cube, u square, u1 multiplied by -1, 3, -3, 1, 3, 6, 3, 0, -3, 0, 3, 0, 1, 4, 1, 0, and here we will get 4 terms, which will be pi minus 1, pi, pi plus 1, and pi plus 2. Okay, this term, this is for k equal to 4. Okay, and this formulation I have said we are using when I is between k and n. Okay, not for all the values of I. Okay, only when I is between these two can we use this formulation. Okay, what that basically means is that my curve has one formulation in this range and this range, but at the ends the formulation is slightly different. Okay, that's basically because my shape functions for this point and for this point, the blending functions are different. Okay, and if we want to use the same blending functions, okay, then what happens is that my curve might not start from here, but it will start from some other point. Okay, let us look at the blending functions. This is one blending function we had. This is a second blending function which is similar in shape to this one. Okay, but this blending function we said it has a different shape. Okay, because this portion of the curve is totally different, and then this portion, this curve is also different. Instead of that, if we take the same blending function and truncate it at this point, okay, my blending function can look something like this. Okay, similarly these blending functions will look something like this. Okay, now instead of having the blending function 0, that means n43 was 0 here. Now my n43 is going to be non-zero. Okay, similarly n53 was 1 here. Now it will be non-1, it will be less than 1. Okay, because I am taking the same shape of the blending function and truncating it. If I do that, then at the starting point, my curve will be a combination of this point and this point. Okay, because this curve, this is the weightage to be given to the point P0, this is the weightage to be given to the point P1. I am giving a non-zero weightage to both these points. So a curve will start at some point which will be a combination of P0 and P1. Okay, and such curves are referred to as periodic curves, periodic B-spline curves. Okay, basically what you do in periodic B-spline curves is you take the same shape of the blending function right throughout. Okay, or this expression that we have got, we use this expression for all the parts of the curve. For all these parts of the curve we use the same expression, but as a consequence of that my curve will not start from the starting point, but it will start from some other point. In fact, we can show that the curve will start for k equal to 3. It starts with the point which is the midpoint between these 2 points and ends at the midpoint over here. Okay, so my curve would become something like this. This is a periodic curve, this is a non-periodic curve. Okay, this is periodic B-spline, and this is a non-periodic B-spline. Sorry. Okay, this curve, the one in red is non-periodic, the one in brown is periodic. Okay, what we will do in the next class is that we will see the exact formulation for the periodic curves and see how their properties are different from the non-periodic curves. Right now, just mentioned that we will use the same shape function. Okay, essentially that means is that we will use this formulation to be valid for all values for all the curve segments. Okay, if I look at this curve, my curve is starting here, ending here. Each of these from 0 to 1, from 1 to 2, 2 to 3 and 3 to 4 are referred to as curve segments. Okay, and this formulation, this expression is valid only for a certain set of curve segments, not for all. Okay, if you use this formulation for all the curve segments, then my curve will look like this one in brown. Okay, that means if I have a set of points, the starting point of the curve is here, ending point is here, and the curve is like this. It doesn't start here, it doesn't end here. Okay, and I will get u equal to 0 here, 1, 2, 3 and maybe 4. This part of the curve will be a combination of these 3, this part of the curve will be a combination of these 3, and the combination will be given by this expression. Okay, that is why it is called periodic. That means the same function is continuing again. Okay, we will see some more on some more details on periodic and non-periodic curves in the next class now. Okay.